Hello, everybody. Now, let me go with another important application of time dependent perturbation theory. And this important application is the spontaneous emission in an atom. And to go with this problem, uh, I have an atom. Let me assume that this atom is initially in some excited state. So I have an excited state. Rather, it will be right to write down the state as E. With the energy of this state equals EE. And so I have the state E. And this state spontaneously decays at the lower state. And so the lower state can be called as ground state here. Ground state. So let me take the state G as the ground state. And with the corresponding energy, I would like to choose here Eg, emitting a photon, right? The atom basically is coupled, this atom is coupled to an electromagnetic field, and the interaction Hamiltonian, the interaction Hamiltonian, which is V of t, that is minus d dot E of t, where this d, as we know, is the dipole moment, and E of t uh, is the electric field of the emitted photon. So what we will try to do here is we will track down this problem, and we will use time-dependent perturbation theory to find the probability of this spontaneous emission. That's our motivation. So we have the interaction Hamiltonian. V of t is minus d dot E of t for this spontaneous emission. So what we assume is that the electric field that's here, this electric field is oscillating. So assuming electric field oscillating, and oscillating with the frequency, let me choose that as omega naught. And this omega naught is nothing but E excited minus E ground divided by H bar. Now all I have to do is to write the transition amplitude. So if I write down the transition amplitude, so in this case it will be Cg of t, because the end happens at the ground state for this spontaneous emission from the excited state to the ground state. So we have the state E and the state G. So what's this going to be? This is minus I by H bar, integral 0 to t, then the matrix element, this is ground state, V of t dash, and then we have E, and then e to the power of I omega naught t dash and dt dash. And here this matrix element is nothing V of t dash E, it is minus d dot E of t dash. And this E of t dash is oscillatory in nature. So we can look for that, and what we obtain, we have this Cg of t is minus I by H bar, then integral 0 to t, And for the matrix element, we will be using this minus d. GE will be rather right here from the transition from excited state to the ground state, and then E naught, and we have cos omega naught t dash, and then we have the exponential e to the power of I omega naught and d dash and dt dash. This is exactly following the same track, at least from mathematical point of view, as we discussed the two-level system in which we have had the oscillating perturbation interacting with the two-level system, and where we finally calculated the resonance, where it was having a condition to describe the transition probability from ground state to the excited state. So what we are focusing here is we are focusing on this what we call as on this problem, and we are calculating the the transition amplitude. And we can be sure of the things here, and how we can be sure of those things is a matter of statement that we'll be looking for. So what we have is we have to analyze the spontaneous emission. That's our target of an atom for having a transition from the excited state to the ground state, and we have set up the framework to calculate the transition amplitude using time-dependent perturbation theory, and let's move on from here. Let's move on from here with the result that's already written over here. So what we have here is we have written down this matrix element, and this is our exponential. This is our exponential factor. And if I revise it again, this term, the matrix term, describes how the interaction, the matrix term that we have had, it was G and then V of T dash E, which is basically minus D dot E naught. That's going to give us T E naught cos omega naught T dash. Right. So this term basically describes the interaction Hamiltonian, and how the interaction Hamiltonian couples the excited state with the ground state. And specifically, we have this matrix element equal to this. And here this dGe, which I had symbolized as GE, is the dipole moment matrix. It's a dipole moment matrix element between the states, the ground state and the excited state. And the dot product reflects basically the interaction, strength, and the orientation of the electric field with respect to the dipole moment. And then we have the electric field, and in case of electric field, the spontaneous in this spontaneous emission, the electric field can be approximated as E naught cos omega naught T dash. So the oscillatory nature of electric field corresponds to the electromagnetic wave emitted as the atom makes the transition from excited state to the ground state. And then we have this exponential factor. This exponential factor, this term basically accounts for the phase. It accounts for the phase evolution of the system as it makes a transition over the time from excited state to the ground state. This vector, e to the power of I omega naught t dash, describes the oscillatory behavior of the quantum state as the atom interacts with the electromagnetic field. Now, what we do is we use the same technique to integrate this integral, and for that I think there will be certain things that will come out. Cg of t, this minus will make it plus, so you have iota here. This dge will come out, then e naught will come out by h bar will come out, so inside will be left with 0 to t cosine of omega naught t dash, and then e to the power of I omega naught t dash, and then we will have dt dash. And we can again use the trigonometric identity. What's that? That is for this cos of omega naught t dash, we can use e to the power of I omega naught t dash plus e to the power of minus I omega naught t dash divided by 2. So now all we have to do is to multiply this with this exponential term. And what we will come up with should be clear. So c g of t will give us I dge, then e naught by twice h bar, because in the denominator there is 2, this 2 will come out, and then I will multiply this with this and this with this. So what we'll obtain is the integral from 0 to t, then e to the power of 2I omega naught t dash plus the other term will give me e to the power of 0, and then dt dash. Now this integration leads to the two separate terms. This will be the term number 1, and then we'll have the term number 2. The first integral corresponds to the rapidly oscillating term. This is rapidly oscillating term, and which we expect to average out over time. This will average out to 0 over time. And the second term, this term times 1, corresponds to a constant term. So what's that? Cg of t is I dge e naught by 2h bar. And this is the term that contributes to the transition probability. So this is the result of this problem. But we would like to have some physical interpretations of this spontaneous emission. And what's the nature of this spontaneous emission? I mean, spontaneous emission is a quantum phenomenon when an excited atom loses energy to emit a photon without any external perturbation. You're not doing anything from outside. It's fundamentally probabilistic as described by the quantum mechanics, and involves the interaction of the atom's dipole moment with the fluctuating electromagnetic field. And if we talk about the same problem in the quantum field theory perspective, from quantum field theory point of view, the electromagnetic field contains 0-point fluctuations, which can induce transitions even in the absence of an external field. This is why spontaneous emission can occur. And I think I have described the phenomenon of spontaneous emission using quantum field theory, where we automatically lead to a result where you don't have an electromagnetic intervention for spontaneous emission, but it's those 0-point fluctuations that are responsible for executing this spontaneous emission, even in absence of the external field. And we had a dipole matrix element in this problem. The dipole moment matrix element that plays a crucial role and in determining the likelihood of the emission. A larger dipole moment indicates a stronger coupling to the electromagnetic field, enhancing the probability of spontaneous emission. The result of integrating the transition amplitude will ultimately yield the transition rate for the spontaneous emission, leading to the understanding of how quickly an excited atom is expected to decay to its ground state. This rate is governed by, probably by Einstein's A coefficients, which quantifies the spontaneous emission probability per unit time. So to summarize this problem, what we have, we derived the expression for transition probability for spontaneous emission, and it involved analyzing the interaction Hamiltonian and how it couples with excited uh, and the ground state through the dipole moment, incorporating the oscillatory electric field due to emitted photon, understanding the exponential phase factors that dictate the time evolution of the states. The resulting amplitude basically reveals the quantum mechanical nature of this spontaneous emission, certainly highlighting the importance of resonance, dipole coupling, and the probabilistic nature of quantum transitions. And this sets the stage for calculating the transition probability and understanding the dynamics of atomic decay processes. So with this, I would like to say you goodbye.